So my name is Alex Schroyer. I'm advised by Martin Sweeney, and my project is Better Tools for Hardware-Software Co-Design. And another way of thinking about that is accelerating hardware accelerators using machine learning. So we've got basically outline here. First, the problem. The industry standard tools, anybody who's used Vivado knows, are very big and very slow. So some of that is because of essential complexity. The tools themselves have to do a difficult job of understanding all the different FPGA designs, doing place and route, the NP complete problem, and there's also some internal or incidental complexity. Like the tools have lots of features, not necessarily features you want, but the features that some customer asked for and are in the product anyway. At one point, one of our grad students found a copy of a Xilinx employee's home directory included in Vivado. That sort of thing doesn't get in there on purpose. It gets in there because it's so complex that nobody can find those problems. The current Vitis or Vivado 2019, that's how you get Vivado 2019, or one way you can get it is a part of this package. It contains a complete copy of TensorFlow and a complete copy of Caffe, which even if you don't use them as part of the software package, there are checkboxes you can check to reduce the size of the download, but it's still pretty big. So over time, from 2012 to 2019, it's been growing about like this. The interesting thing is that the size of disk space has been growing also. So it's possible that this can continue to grow and you won't ever have the problem where Vivado is too big to fit on anyone's computer. But it still makes it slower. So one of the main problems is everything's written to disk. Part of the reason is it's written to disk because it's big and it doesn't fit in RAM. But that makes everything slow, makes developing for people like us difficult because NFS storage doesn't work very well over a connection like this. Bitstream generation takes a long time because it's writing many intermediate files, often the same files over and over again for every different design you do. And for every different change you make, it writes the same files again. So those are some of the problems. So the goals are better, faster design workflow for people like you working in this space. So the priorities for us are different from the priorities of FPGA Professional. FPGA Professional wants optimized builds. They want legacy part support. People like us want to do iterative design, lots of little small changes, and often we're only going to do something on FPGA once as part of our graduate school career, and then maybe never use it again. So becoming an FPGA professional is not something for everyone. So we don't need to have a tool that is for FPGA professionals. We need something that works well for us. And this is part of the problem. Long compile times change the way you think about what to do because it makes you more conservative. It makes your changes more costly. And so short compile times let you iterate faster, let you do experimentation. You can throw things away more easily if your compile times are short, which means you can not be stuck doing the wrong idea for so long. So some of the solutions, or the solutions that I'm proposing, are to use test benches as training data. So test benches are something that often we write ourselves, but they could be generated from type information in the input language. And using generated place and route, which is typically not part of a test bench, but my idea is to make this also automatically do some place and route as part of the compile. Using that generated place and route as training data for some recurrent neural network will give a place to see which optimizations are more useful than others. As an example, Google's recently started working on this problem for ASIC design, and they found that neural network assisted place and route has a very different look for their chips than a place and route design done by a person. So this one's very regular. It's got also has longer path lengths and worse congestion than the AI-assisted one. The other main things that I'm going to use as a technique to make this actually feasible within half a semester is to shrink the problem quite a lot. So I'll only be supporting one part. I'll constrain the optimizations that I want to do to just delays and wire length. I will map the designs to a specific area of the FPGA. This is something that can be done in using Vivado tools. And using the existing place and route, I will generate the training data for more optimal place and route. And by optimal, I mean faster. Faster to finish the place and route design. So my timeline is I have a colleague who has a bitstream generator tool. So that generates a bitstream for Xilinx FPGAs. And so this is a reverse engineering tool, but my use of that will be to adapt it as a bitstream generating tool. And then a week to adapt an existing compiler, which compiles to Verilog and VHDL. That'll be used for input generation, or input HDL code generation. I'll use a bit of time to benchmark the design that was in the project in this class, the 16-bit adder subtractor, benchmarking in terms of wire length, path delay, and then a bit of time to re-implement that same thing in the HDL for the compiler workflow. And then some time generating test bench training data using Vivado's existing tools, varying the placement and routing parameters, varying the costs, and that will be a way to generate tagged data using Vivado. And then finally, a week to remove the Verilog stage and compile it directly from the intermediate language they'll be using to the Xilinx bitstream. So those are some solutions I propose. The evaluation for this will be simulate HDL and test benches for an example circuit, and then compare resource usage from Vivado's to the optimized design. So the comparison there will be not just in the effectiveness of the end design, but also in the speed of compilation. So also we'll compare defect rate if the design doesn't work, kind of does not pass, and create projections of overall design time costs for people like us who are doing these kinds of designs. So I have some references here, and that's it. Any questions?
Who or what inspired you to do this?
Using Vivado has inspired me to do this.
You have a very good sense, but reducing compilation time is not attractive. I can tell you this idea can be published. This is a very emerging so-called automatic optimization stuff for FPGA design. You need to revise the problem, not optimize for reducing the compilation time, but optimize for something else. If you are interested, we can talk.
Okay.
We can talk. For example, you can automatically design a pipeline structure for some application, for one application. For example, I don't know. I know Martin is working on some networking application. You can design a pipeline, automatically write a tool to design the pipeline for that networking application. Because on the FPGA, you have a lot of on-chip resources and off-chip resources. You need to do loop unrolling, those compilation optimizations. You don't know. Maybe there are a lot of knobs configurations you can try, but you need an automatic tool to do the design space exploration for you. Maybe that's more interesting. But you have already see the genetic algorithm, right? You have the reference.
This one?
This one and the last page you showed me. The genetic algorithm. They try to use some those automatic in machine learning based tool to explore the design space. You can take advantage of the deep reinforcement learning stuff like the AlphaGo. You know, it's like it's not instead of playing a Go, you can do the design by some definition. This is a very good topic, but you need to do some refinement.
Narrow.
That's right. That's right.
I see what you're saying. I'll find
yeah,
that topic.
sure. Thank you very much.